Hey, Anna. Feel free to ask me any questions you might have. All right, everyone. We got a little bit of time left before class starts, only about a minute. Anybody have any questions before we get started? I did make it back to class today, so finally I was in the building. I hope some of you were able to attend. I know Hannah did, but I now see there's two Hannahs, so I'm really confused. Namely because I haven't learned my role yet, but uh, that's often the issue. Horrible with names, but anyways. Looks like we've got just about, it's still pretty short. We're only about 7 students in. We need a few more, but I guess we should go ahead and get started. We are in chapter 3, specifically the part of chapter 3 where we're still working on vectors. So I wanted to start off by recapping what we learned so far, just so you'll understand the importance of this particular topic. So we're going to do this and sort of blow through this, and then I'm going to jump into a really fairly robust addition of vectors problem and further that discussion of different ways you can specify vectors in ways that are way more efficient. Okay. So hopefully that'll be helpful to you guys. And it's completely consistent with the book's doing, so you don't have to worry too much about me, deviating and going over some crazy stuff. But first off, let's go ahead and share the screen while we're waiting for more people to come in. We've got 9 in here now. Feel free to ask me questions while I'm in the process of getting my screen to share. Okay. It's coming up hopefully any second. There it is. All right. So we basically had two things that I had helped you guys figure out. There's two typical positions in which you draw vectors. You can draw the vectors head to tail as they're shown in the top left and the top right, or you can draw. Ooh, I just realized I drew the top right in correctly by some mistake, so I'll fix that. Or you can draw them tail to tail, as is done in the bottom left and bottom right. Only that one I actually did correctly. Well, dang it. I just bumped my arm with my other arm and it made me erase too much, so I had to fix it. Okay. Now that's pretty good. That looks all right. So these are supposed to be head to tail. That means my B vector should be like that. Now I've got them set up correctly. And now we've got more people coming in. So first off, I wanted to talk to you about adding vectors when they're head to tail and then adding vectors when they're tail to tail. So if you look in this case, remember our archetypal example of adding vectors was you walking out of your front door of your house or your apartment or whatever, going across your yard and stepping onto concrete, asphalt, cement, whatever it is. That could be a parking lot, that could be a road, but the main thing is directly in front of your door, you can imagine a little nail in the asphalt or in the concrete or in the yeah, whatever. Uh, but that nail is going to be like our origin. And if you were to stand back at your front door and look at where that nail is, it'd probably be instinctive for you to call the right direction the positive x-axis, maybe the up direction the positive y-axis. And what I use as the archetypal definition of addition of velocities, or excuse me, of addition of vectors, was you imagining walking along some straight path from that little nail in the concrete to the right or to the left. That was one dimensional, of course, and that was a purpose in us doing it. So if you walk a straight line to the right or to the left, that straight line represents the first vector, and that's the vector that took you from the origin to your first location, which you finished after you completed that walk. Then at the end of that walk, you could take another long straight walk or short straight walk. The main thing is straight. Okay. And if you did that, then that would draw another vector, not unlike the vector B. Notice that that vector B has its tail, its starting point at the end of, or the head of vector A, which is the end of your first little trip. Okay. If you have it that way, then you're automatically done because the vector addition is supposed to be drawn from your initial position to your final position. So you can immediately see that A plus B is just that. That is A plus B, which we often call the resultant. So sometimes you'll see R there uh, for resultant. Okay, so that's some more terminology we use because it saves us a lot of time and writing where we don't have to write A plus B plus C plus D. No matter any number of vectors you add together, the sum of that is the resultant. So it's a really wonderful saving of time. Now, if you consider two vectors tail to tail, that's different. We have a little bit of problem with that. But if you remember my definition of a vector, it should be remembered that I said a vector is something that has direction and magnitude, not unlike vector on Despicable Me, right? So if you think of that as a definition, it probably seems pretty reasonable that as long as you don't change the magnitude or direction of the vector, then you haven't changed the vector. And that's certainly okay, long as we're talking about everyday physics like we're doing now. Later, we'll learn about vector fields, and that's a whole different story. But the main thing is, let's just think about a vector in space. And as long as you don't stretch it or compress it, which changes its magnitude, and you don't twist it from pointing one direction to another, which changes its direction, then you haven't altered the vector. So you might think to yourself, well, what if I were to slide vector B along A until it became head to tail? That's exactly what we want to do. So what I'm going to do is I am going to imagine sliding vector B. So I'm going to think of it as having a little loop around the end, and A can act like a little slider along it. And when I do that, I get another vector B here. Okay. Similarly, I could think of that little loop being on vector A and being wrapped around vector B, in which case I would say that this is where vector A is. So if we wanted A plus B, what I would focus on is the fact that the top half of that diagram I now have has A starting from where that little circle is, going to the end of its arrow, and then at the end of its arrow is the tail of vector B, which goes down and to the right to this point right here. Everybody see that? Okay, so that's the very definition of our vector that we learned from head to tail. So in fact, we can go ahead and say that A plus B is that vector. Now, the terminology we use here is called completing the parallelogram. So it wasn't a parallelogram before, but as soon as you take B and slide it along A, then you get B and the other copy of B being obviously parallel to each other. And then as soon as you slide A along B, you get A and the other version of A being opposite and parallel to one another. So it does make a parallelogram. Not only that, you can see that if I instead wrote B first and then A, then I would have to use that bottom half of the diagram, and you'd see that B plus A is the same thing as A plus B. So this is also proof that A plus B is equal to B plus A, which is what I told you about some of those weird little rules in pre-algebra and high school algebra 1. A plus B is equal to B plus C. Okay. So obviously, to add two vectors that are tail to head to tail, you start at the head or the tail of the first one and draw to the tail of the last, and that's your resultant. No matter how many vectors there are, I did it for two vectors, but if you did 50, still be the same thing. You just go A plus B plus C plus D plus E plus F and keep on doing until you got the last one, and then you draw a line from the tail of the first one to the head of the last, and you've got the result. Does that make sense to everyone? Now, tail to tail is a little bit more complicated, and in fact, you can only take it two vectors at a time when you're doing it this way. In this case, what you do is complete the parallelogram, and then you draw a vector from the common tail to the diagonally opposed vertex. So from common tail to So in other words, you just go across the opposite to the diagonal, use the diagonal across the opposite corner, across to the opposite corner, and that's where your vector is going to be. And it's important that you realize the arrow is over there at the right-hand side, not the left-hand side in that bottom left diagram. So does everybody follow that? Any questions on that? All right. Now, I've sort of hinted at this a little bit, but we need to be a little more thorough. I am going to use that weird rule from pre-algebra and high school algebra 1 that seemed about pointless when I learned it in pre-algebra, A minus B is defined to be A plus the opposite of B. Notice I wrote the words opposite of B or the additive inverse. That's another word for it, so that's super helpful. So that's what we're going to use. But in order to do that, I've got to understand what is negative B. If that was a negative X, what would be the coefficient of X? Anyone? And I put the chat up now in case anybody answers me that way.
Is it -1?
Yes, it'd be -1. And that's the key point. So what I wanted you to see is that there's a delivery truck here, Shawnee. What I wanted you to see was that negative B is -1 times B. And therefore, I now need to talk about multiplication of a scalar and a vector. So the rules are quite simple. If the scalar is positive, nothing happens to direction. Okay. So if you're multiplying C times A, nothing happens to the direction if C is positive. If C is negative, the direction goes from there to there plus 180. In other words, it flips 180 degrees. Now, the other sort of key points is if the scalar you're multiplying by the vector is larger than 1, then that makes the vector get longer. And I mean magnitude. It's going to get longer whether it's a +1 or a -1. It's just the -1's also going to flip it around backwards. So if you multiply a vector by a scalar that has a bigger magnitude than 1, it's going to get longer. And if you multiply a vector by a scalar that has a smaller magnitude than 1, it's going to get smaller. So you can see right here, I drew the vector A in black. And then notice 2A, instead of going diagonally across a 2 by 2 square, it goes diagonally across a 4 by 4 square. So you see doubling doubling the vector did double the length, obviously, because the diagonal of a 4 by 4 is twice as long as the diagonal of a 2 by 2. But it also, what we'll later learn is it also doubled the X component, which is the 4 little blocks that went along and to the right, and it doubled the Y component because now it went up 4 blocks instead of 2. Okay, so that's something else to keep in mind. If I instead multiplied A by 1/2, now it's just a 1 by 1 square across the diagonal. So you see the 1/2 A is literally half as long, but still pointing in the same direction. If I drew negative A, all I do is take the head off the top right end and put it on the top, or excuse me, the bottom left end. Does that make sense to everyone? So with that in mind, we're now in a good position to introduce the opposite of B. Okay. So if you'll look, I've got A and B in the top right. I've got A and B in a head to tail configuration. The tail of B is at the head of A. So just in case anybody's wondering, the head is the arrow part and the tail is the loose end. And they are to head to tail. So if I want to actually subtract them, the first thing I'm going to do is replace B with the opposite of B. Okay. Well, doing that's all fine, but now I've got them head to head, and we've not learned anything about dealing with vectors head to head. But we certainly learned in the bottom left that you can slide a vector along another vector without changing anything. So what I'm going to do is I am going to imagine sliding that vector along there, and I'm also going to imagine sliding the A vector along here. Or excuse me, yeah, the A vector along here. So we can do that, and when we do that, we get an A again. And of course, when we do that over here, we get a negative B again. Notice I put the head on the left-hand side. So now you see that negative B in red and A in blue are actually head to tail. So my rules are just do what I did with the head to tail, which is draw from the head of the from the tail of the first to the head of the last. So I'll write that here. Draw from tail of first to, let me make that more clear, actually, to the head of the last vector. Okay, so now I can do that with the red negative B and the blue A, and in fact my answer will be right there, and that is the vector A plus negative B, which is A minus B. Does that make sense to everyone? Now, what if we try to subtract vectors, only this time they're tail to tail? So if we subtract vectors tail to tail, again, the first thing I'm going to do is draw negative B. So I'm going to draw a black line right along B, and I'm going to put the head pointing in the opposite direction. And now I've got negative B. But look, by doing that, I end up putting A and B in head to tail configuration. So I can easily draw A minus B. Okay. So what I wanted you to see, and this is a bigger point regarding math and science in general, what I've discovered in my long life, because I'm so old, I'm like really old compared to you guys. So what I've discovered in my long life is often you'll have one way of doing a problem and some part of it will be really easy. But often what happens is some other part of it will be really hard. And if you end up trying to do the other way, those roles reverse. So the easy part becomes hard and the hard part becomes easy. That's often what happens. It even happens like in differential equations. Sometimes integrating a differential equation is really hard, but differentiating it is really easy. And sometimes some of the stuff you do after the fact is a little easier if you integrated it as opposed to differentiate it. So little stuff like that comes in from time to time. So maybe that's something you can just keep in the back of your head to think about. But notice how easily we added head to tail vectors. We just had to draw the vector. So this is super easy, which I'm going to break all out and say, even in a different color, super easy. So adding two vectors head to tail is super easy, whereas subtracting vectors that are tail to tail is super easy. So hopefully that'll help you keep in mind exactly what procedure to do. Anybody have any questions on that? All right. So now what we're going to do is I've already shown you how those scalar times a vector has very specific outcomes. And in fact, one of the nice ways that you can actually write vectors is you can pretend there exists a little unit vector pointing in the positive x direction. And when I say unit vector, I mean its length is 1 unit, not 1 meter, not 1 meter second per second, not 1 Newton, but literally just a unit, like the number, right? So if you drew a vector in the positive x direction, you could call that X with a hat over it, because the hat, which looks like a greater than symbol or like a dunce hat. Okay. That hat indicates to people that know about vectors, that indicates a unit vector. Okay. So you could call that X hat because it's in the X direction. But traditionally, what we've done is we've called that one I hat. Similarly, you could draw a unit vector in the positive y direction, and you could call that y hat, or traditionally we've called it j hat. And then you could do another one for the z direction, and that'd be called z hat or k hat. So when you have a vector, if you know it's in the x direction, you can just multiply its magnitude times the I hat, and that's a way to write the vector completely. You don't have to write any directions or anything like that. If you have one pointing in the y direction, you can just write the magnitude times the y. Now, it should include the units because the units aren't coming with the unit vector. So, for instance, if the vector is in meters per second, you'd want to take the magnitude in meters per second and multiply that by the I hat to make a vector pointing in the x-axis in the positive x direction. If you wanted to point in the negative x direction, you just put a negative sign in front of it. So negative 1.2 meters per second I hat means it points to the negative x direction. If you have a vector that has both an x and y component, as all these vectors clearly do, then you take and figure out what the x component is and put that in front of the I hat, and you take and find out what the y component is and put that in front of the j hat, and even do it for the k hat if you have a z component, and then you just add them. And that's the unit vector notation that your book is introducing you to. I'll show you some more of that later, but I just wanted to use that little diagram of the scalar multiplication of vectors to help you figure that out. So now let's do a vector, specifically a vector sum. Now, if you look in our Canvas course, you'll see in week 3, there is world's greatest vector addition problem from 9/27/20. And you see vector and projectile problems, subtracting vectors by drawing, adding vectors by drawing, 4-vector addition problem. Notice that one's a little newer, though it doesn't say the greatest vector addition problem in the world. It is newer, so it will be a little better. But all 3 of those videos are really good for helping you. What I'm going to do right now is do an actual vector addition problem from scratch. And I've already taken the time to write the vectors, and I've even taken the time to show you 3 special triangles that will allow me to do the computations without using a calculator. I do not want you guys to assume that you have to do that, okay? I just want you to find the component using your knowledge of trigonometry. That could be SOHCAHTOA, or some old horse came a hopping through our alley. However you want to do that, that's fine. And what I want you to do is, at least until you're really comfortable, go ahead and take the time and write sine of 36.87 equals opposite over hypotenuse, and then put in the name of the opposite, the name of the hypotenuse, and then write cosine of 36.87 equals adjacent over hypotenuse, and put the name of the adjacent and the name of the hypotenuse, and then solve each of those to figure out which one's the x component, which one's the y component. Do that all you want, okay? And you never have to stop doing it. But like I said, as time goes by, you might be able to do it by skipping that step, and that'll save you a little time. And you might even be able to do stuff like I'm going to do here. So let's start off. I'm going to draw a coordinate system. And actually, I'm going to draw a coordinate system repeatedly. So there's my y-axis. Now I'm going to try to move it and make it right along a line. And then I'm going to draw a x-axis like this. And I'm going to move it to put it right along a line, or I'm going to make it stupid and put it at some angle like a gooby head. Okay, so that's my x-axis. Well, actually, let me change my writing. So this is going to be an x-axis, but what we'll find out is that's also normally the east direction, which is a compass heading of 90 degrees. This is the y-axis, but that's normally the north direction, which is a compass heading of 0 degrees. Down here would be south, which is a compass heading of 180 degrees. And y'all can look up a compass if you want to double check that, but that is the way we do it. And this is the west direction, and that's 270 degrees. And in fact, the north is also 360. That makes sense to everyone? Okay, so that's sort of the precursor to what we need in deciphering these vectors. So I told you, for instance, that problem that I put on Canvas, world's greatest vector addition problem. What I mean by that is I took the time to make sure I had a vector from each quadrant so you can select the positive and negative signs appropriately for their components. And I chose each of the four ways I could possibly specify a vector direction so that you can get the hang of that. So first off, we're looking at 20.0 meters at 60 degrees. The fact that it's 60 degrees tells me it's probably related to that bottom left triangle, and that's true. I'm going to use that. Okay. So what I'm going to do is I'm going to draw this vector, and I shall draw it in, let's draw it in black. No, let's draw it in blue. I'm going to draw it in blue. Okay. So it's going to be at 60 degrees. And notice if it just says at and then has a number, whether it be positive or negative, that's understood to be the mathematical or the trigonometric way, which means you measure your angles counterclockwise from the positive x-axis, and that's a positive angle, or you measure it clockwise from the positive x-axis, and that's a negative angle. So just for the record, I can draw that down here. Oops. I can draw that down here like this, and this, and this angle right here would be a positive angle, whereas this angle right here would be a negative angle. Okay, so that's the standard position of angles as we use in trigonometry. So A and in fact D as well are both that type of one. Okay. So what I'm going to do is roughly estimate what looks like 60 degrees. And that looks pretty good. I might have went a little bigger than 60 degrees. And I'm going to call that 20. And that's going to be my vector A. And this angle right here is 60 degrees. Now, if I cut that in half, which looks roughly right about there, and then I cut that in half and cut that in half, then I can see this little length should be about 4, roughly. The length from the origin to that spot should be about 4. And then, well, actually, all those went kind of poo-poo. Let's make it a little better. So there's my, I'm just trying to make up a scale where it looks pretty good. That looks pretty good. Yeah, that's not too bad. So now I've got an idea of exactly what 5 looks like. So 5 should be about the length from the origin to that first hash mark on it. Okay. Now, the next thing I do is I draw another coordinate system right at the end of vector A. So I'm trying to be very meticulous about this. I don't know why, because the chances of me getting a fairly correct answer with this without using protractors and all that is slim to none. But now I've got to put vector B, which, by the way, that's A. So let me go ahead and label that A. Oh, Nelly. That's A. Now, vector B is supposed to be 25.0 meters per second, but this one's at 36.87 degrees west of north. By the way, west of north is entirely different than north of west. North of west would be just barely above the west axis towards the north, and west of north is just barely to the left of the north axis towards the west. Okay. So in this case, I'm doing west of north, and I need it to be 25 meters, 25 meters per second, which roughly gives me about there. So I have an idea roughly where I'm going to draw it to. Okay, that can't turn out crappy. Let's try another one. Okay, that looks pretty good. Not perfect, but pretty good. Ooh, Nelly. Okay. That looks fairly good. And that should be roughly 36.87 degrees there. And this is vector B. Now I used the scale that I had to draw roughly 25. So this one should be about a quarter longer than the vector A. Now I got to draw another coordinate system right here, which I'll draw just like so, and just like so. Okay, so that doesn't look too terribly bad. Now this vector is a compass heading of 225. Now, according to the drawing, if I went straight up parallel to the positive y-axis, that'd be 0 degrees. If I go straight to the right, that's 90. If I go straight down, that's 180. If I go another another 45 degrees, then that'd be 180 plus 45 is 225. So that's what I need is I need to split the negative x and the negative y axis in that new coordinate system I drew and try to make something that's about 2/3 the length of the first vector. So I'm going to say roughly here. And now I'm going to attempt to draw that vector. Okay. Now this one has 45 degrees right there. And that vector is C. Okay. Now I got to draw another coordinate system at the end of that. That looks pretty good. I'm going to delete that guy. Okay, I'm not going to delete that guy. Plus, I don't remember how to delete. But anyways, that'll work. See if I can get a delete to come up. I do not get a delete to come up. That's not helpful. What about that? Whoa, Nelly. Nope, don't want that. Oh, well, I'll just leave it. It's good enough. Okay, so at the end of vector C, I got to put vector D, which is supposed to be the same length as the second vector, only this time it's negative 36.87. So my vector should roughly point somewhere around in there, or at least that length. Now I'm going to try to draw the vector to that spot, making sure it's a little bit bigger than 30 degrees. And of course, I'm going to forget to make it neat, so that happened. Okay. And that, in fact, is vector D. Okay. And this angle right here is 36.87 degrees. So everybody follow what we did there? All right, so what I'm going to do is show you what the resultant is. Remember, the resultant is the vector that's drawn from the tail of the first to the head of the last. So in this case, the resultant is that vector right there. And that's R is equal to A plus B plus C plus D. Okay, now how do we go about adding this? Well, this is where I am going to make use of my knowledge of vectors now and special triangles. So I clearly have a special triangle with vector A.
And in fact, if I wanted to walk from the tail of vector A, which is that little blue guy right next to R, okay, if I wanted to walk from the tail of vector A, but only by going along axes, then I could either start by going up or I could start by going to the right. Uh, by going to the right, which is the direction I've chosen, I can just draw right here like that. And since it points to the right, I know that is the positive direction, and that's my A sub x. And now I want to proceed still towards the end of the vector. And again, I still want it to be parallel to a axis. So I'm only left with going upward. And in fact, that's my A sub y right there. And both of them point in their positive coordinate directions. So they're both going to be positive numbers. Okay, now here's where I was telling you guys, I would just, until you get comfortable with this, maybe you should just do something like writing. Actually, no, I don't want that color. Let's do this color. What I want you to do is say the sine of 60 degrees. And remember, sine is opposite over hypotenuse. So that's going to be AY over A. And then I'd take the time to write cosine of 60 degrees. And that's adjacent over hypotenuse. And adjacent means touching. Okay. So that's AX over A. Okay. So by writing those down, then you can see how to solve for AX and how to solve for AY, but you still have to put the signs on it. So you got to keep that in mind. But what I'm telling you is go ahead and do that. That's fine. You can go ahead and write that down, compute what sine 60 is. Obviously, AY is going to be A times the sine of 60. For us, what I know that means is notice A is 20. And if we look at the special triangle that represents it, the hypotenuse is 2. So obviously we have to multiply those by 2, which means the x component, instead of being 1, is in fact going to be 10. And that's meters per second. And the y component, instead of being 1.7321, is going to be 17.32. And actually, let's go ahead and pretend like we're doing everything sufficient just to have two decimal places. So I'll write this as 10 meters per second. Okay. Everybody understand how I got the x component and the y component for that vector? Don't get bogged down by me using these special triangles. It's just me avoiding using a calculator because I'm wanting the class to roll. Okay. So in practice, you could write sine 60, which equals root 3 over 2, which equals 0.86605. Okay. You could say is equal to 20 times 0.8605, and that's equal to AY. And you'd get roughly 17.32. Cosine of 60 degrees is 1/2, and you multiply that by 20, you get 10. So AX is 10 times, is actually equal to 10, which comes from basically 20 times 1/2. Okay, so that's really what we're doing. Now for vector B, you guys might want to take the time and try to figure out those components yourself. Specifically, just figure out which directions they point and draw them. Don't even worry about the magnitudes yet, but draw them so you'll know whether they point left, right, up, or down. I'm going to do the same. These two, one points in the positive direction, the other one points in the negative direction. So I know it goes in the positive y direction, which means I am going to draw from here straight to there. Now that went horribly, so I'm going to do it again. Okay, so that vector is B sub y, and clearly it's a positive, so I'm going to force that positive on it by sticking that positive sign there. And then notice I've got to go to the left to get to the end of the vector, and that's a negative direction, which I use red for. So I'm going to draw this way. And this is b sub x is equal to a negative number. Now we can look and see that that's 36.87. So that's our 3, 4, 5 triangle. And of course, the hypotenuse of the 3, 4, 5 triangle was supposed to be 5, but for RB, we had 25, which means I basically multiplied that 5 by 5. So I've got to multiply the 5 by 3. That'll give me 15, which is supposed to be the opposite of the 36.87 degrees. So the opposite of 36.87 is the x component. So I'm going to write that as negative 15.00 meters per second. And then the adjacent side to the 36.87 would have been 4, but we have to multiply it by 5. So that's going to be 20.
And is that calculating the magnitude?
Yeah, so what I'm doing is you can think of it this way. Try it with your calculator in real time. Take 25 and multiply it by the cosine of 36.87, and you should get roughly 20. It might be 19.999 or 20.0001. Everybody see that?
And where
Now
did you get the 28? Oh, sorry. Where'd you get the 28.7 from? From the
the 36.87?
Oh, 38. Sorry, yeah. Okay, I see that. Thank you.
Yeah, that came from the special triangle. If you do the inverse tangent of 4 over 3, you'll get 53.13. And if you do the inverse tangent of 3 over 4, you'll get 36.87. Okay. I'm just making use of those angles because I know them, right? All right. So I think at least Jen was able to verify that the 30, or excuse me, the sine of 36.87 times 25 gave me 15.00. And then, of course, you artificially have to put the negative sign on. But notice the way I'm doing this is I never have to choose an angle that's greater than 90 degrees. And I always get to figure out whether the sign is positive or negative. It doing it automatically makes sort of a black box, which means you're just subject to whatever errors your calculator does or whatever errors there might be in your understanding of trigonometry. So let's let you guys try for the components of C. At least draw them and then use your trig functions to calculate them, and I'll write them down. Okay, hopefully everybody got your x component pointing to the left and knew that was therefore negative, and had your y component pointing down and therefore knew that was negative. Anybody not get that? Now, where I drew my triangle, that might not look natural to you, but remember the sum of those angles there on each side of the vector C is 90, so the other one has to be 45 as well. So I can just write 45 there, and then everything's kosher. Okay. Not technically kosher, but that's, everything's fine. All right. So what I know is generally that's the 1, 1 square root of 2, or the 45, 45, 90 triangle. And of course, that has a leg of 1, another leg of 1, and 1.414. If you'll notice, my magnitude was 14.14, which looks a lot like 10 times the square root of 2. So clearly these two components are just going to be 10 and negative 10 and negative 10. So this is 10.00 meters per second with a negative, and 10.00 meters per second with a negative. Everybody get that? All right, now we got vector D. And vector D, obviously, I'm going to start from the tail and I'm going to try to draw draw green lines that are positive and red lines that are negative. So if I want to go from the tail of D to the head of D, I can start off along the x-axis by going to the right. And that's what I'm going to do. And that's an actual positive direction. So I'm going to use green. And I'm going to cheat and use the computer's ability to draw this very nicely. Whoa, I don't know what happened there, but that was not what I wanted. Whoa, Nelly, that was bad. Let's undo that one because that did not turn out the way I liked it. Okay, so let's draw again. Right about there. That looks pretty good. And now I'll put my arrow up there and that'll make the extra distance. And that's going to be D sub x. And of course, that's pointing in the positive direction. So I'll put a positive sign on it. Now, if I want to still get to the head of D, I've got to go parallel to a y-axis, which means I got to go down. And down is a negative direction. So that means my y component is right here. Of course, it makes a look like a moron when I do it. Well, stop doing that. Ah, stop doing I hate that. You go away. I'm just going to draw it myself then. Yeah, that actually turned out a lot better. Okay, so what this says is D sub y is actually a negative value. Now, again, notice that's a 36.87. If you see like a 37 degrees or a 36.9 or something like that, that's your author or whoever made the question trying to tell you, hey, this is a 3-4-5 triangle. Same thing if you see a 53 degree or 53.1 degree or something like that. So in this case, we actually had the magnitude was 25, which is, remember the magnitude of the hypotenuse of the 3-4-5 triangle is 5. So we're just going to multiply those by 5. So the angle that's adjacent to the 36.87 will be 4 times 5. Or excuse me, the side that's adjacent to the 36.87 is going to be 4 times 5 or 20. So that means dx is positive 20.00 meters per second. And then the opposite would be the 3 times 5 or 15. So in fact, I think I'm going to draw this dy somewhere else because that doesn't make it easy to write in here. So what I'm going to do is say, whoa, Nelly, is say d sub y is equal to negative 15.00 meters per second. And then I'm going to say that's that guy right there. Okay. So you see what we've done? We've managed to take each of the 4 vectors and put them in component form. The beauty of component form is x components just add with x components like positive and negative numbers. Y components add with Y components like positive and negative numbers. Z components do the same thing. So once you've got them to components, you're just doing basic arithmetic for the components, and then you got to rejigger everything to get it right at the end. But that's not a big deal, as I'll show you. So what I'm going to do is, and some people actually make a table here. I did that in my lecture today, but I think it caused more problems than it helped. So I'm not going to do that. But you can certainly do a table if you like to keep your mental math a little bit cleaner. But what I'm going to do is say A sub x, B sub x, C sub x, D sub x. And then those added together give me R sub x. Okay, so our A sub x was positive 10.0, and I'm just going to put meters per second over top like this, so I don't have to write the unit every time because I'm kind of lazy. Okay. B sub x, notice that goes to the left. This is a good time for you to check to make sure all your signs are right. So that's negative 15.00. C sub x goes to the left as well. So that's negative 10.00. And D sub x actually goes to the right. So that's going to be positive 20.00. You can see that the negative 10 and the positive 10 cancel out. So I just get 20 minus 15 is 5. So I'm going to write this as positive 5.00. So that's the resultant x component. Now, just to keep it different, I'm going to write A sub y, B sub y, C sub y, D sub y, line R sub y. Okay, so A sub y, again, checking to make sure everything looks right. That is in the first quadrant, which means the y component's positive, and that's positive 17.32. There's the decimal. And I'm going to say all of these have units of meters per second. B sub y is positive 20. So I'm up to 37.32. C sub y is negative 10. So now we're back to 27.32. And then D sub y is negative 15. So we had gotten up to 37.32 minus 10 to be 27.32, minus 10 would be 17.32, and then minus 5 would be 12.32. So I got 12.32 as my y component of my resultant. Does that make sense?
Was that a minus 5 or a minus 15?
That's a minus 15 at the bottom. Okay. So how do we do this? Well, I gave you the vectors in magnitude and direction notation. So I assume that you're going to give it back to me in magnitude and direction notation. If I'd given it to you all in IJK notation, then you can put it all, you can return it in IJK notation. But when I give it this way, you need to assume that. The good news is most of our tests are going to be multiple choice. So you'll just have to match whatever choices you're given. Now, how do I do this? Well, what I want to do now is I need to actually draw a coordinate system again and make some sense out of what this vector looks like. So to draw a coordinate system, I am going to draw that line there and this line here. And I'm not using this quadrant. That's why it didn't matter. So I put it over here. This is going to be my x-axis. This is going to be my y-axis. And notice my x component is basically positive 5. So what I'm going to do is I'm going to say that maybe 2 lines is equal to 5. So that's positive 5.00 meters per second. And then my R sub y is 12.32, which is a little bigger than twice 5. So in fact, I've got to maybe make the R sub y go up here. And that one's going to be 12.32 meters per second. I've got the vectors tail to tail. I know how to deal with that. I'm going to complete the parallelogram like so. And in fact, my vector solution, which we drew as purple before, so I'm going to draw as purple now too. That's going to draw from here to here. And that vector is, in fact, R vector. And I'm going to call this angle phi. Now you can see R is the hypotenuse of a right triangle, right? So what you can write is the R vector in absolute value bars, that means magnitude. If you're in a math class, often they end up using this to mean magnitude. If you're in a physics class, we really like doing everything fast and loose. So if I just drop the arrow, then everybody understands that's the magnitude. So that's the easiest way for me to represent the magnitude. And I have to take the positive square root specifically because magnitudes of vectors are always positive. What I'm going to do is I'm going to take 5.00 meters per second and I'm going to square that. And then I'm going to take 12.32 meters per second and I'm going to square that. And I'm going to take the sum of those two and take the square root of that. And when I do that, I get 5 squared plus 12.32 squared. That gives me 176.7824 meters squared per second squared. And I'm just trying to show you all the gory details of what's going on with the not only the units, but what's going on with the sig figs. So notice when I took 5 and squared that, that would become 25. I only had 3 sig figs to work with. So 2 of them are expressing the 2 and the 5, and then another one expresses 1 decimal place. So I only get 1 decimal place as a result of 5 squared. The 12.32 is going to be like 140 something. 3 of those digits are in the 140 something, so I'd only get 1 decimal place there. So in fact, I really only get 1 decimal place, which means all those are not significant digits. So now I'm going to take the square root of that answer, and that gives me, notice, because I only went to 1 decimal place, I now have 4 sig figs. And when I take the square root, I get 13.296. And that's meters per second, because the square root of meters squared per second squared is just meters per second. Clearly, I'm only supposed to have 4 sig figs, so that 6 is 1 extra sig fig. It's not a sig fig, it's just an extra digit. Okay? So that's my magnitude. Now, the angle phi, and this drawing helps you if you're actually doing a paper test, having that drawing with the coordinates on there, the instructor can immediately look and say, oh, yes, they did the same thing I did. They just used it in a different coordinate system, so I can tell whether that answer is right or wrong, right? So that's why you always want to show that part. But in this case, what we're doing is taking the inverse tangent, which is what you almost always do if you have the x component and the y component and you're trying to figure out the direction. Now, some old horse is sine equals opposite over hypotenuse. Came a hopping, which is not grammatically correct, means cosine equals adjacent over hypotenuse. And then through our alley is tangent equals opposite over adjacent. The opposite to phi is 12.32. And even if it did have a sign, by the way, I would not put those signs in there. Do not put the signs in there. And then the adjacent is 5.00. And what I get is tangent inverse 12.32 divided by 5, close parentheses. That gives me 67.91. And that's actually 911 degrees. Now, 12.32 had 4 sig figs, 5 had 3, so I only get 3 sig figs. That's why I underline the 2 ones, because they're not significant. So what I can say is R vector is equal to, technically I have to write this as 13.30 meters per second at, notice that angle's already in standard position, so I don't have to put anything extra. I can just say at 67.9 degrees. Now, back to the IJK notation. I could have also written this as 5.00 meters per second I hat plus 12.32 meters per second J hat. If you forget which one's I, which one's J, which one's K, you can also call it X hat and Y hat. That'd be fine. Then there's no ambiguity. But I'll show you an even more succinct way of writing it. You can also write it as less than and technically you could put all the units outside, just write meters per second next to those brackets, and you only have to write meters per second once, or you can put it in each one. All of those are completely valid ways of writing the resultant vector. Anybody have any questions on that? So let's recap what I did. Maybe that'll help you see the big picture a little better. So when you're adding any number of vectors algebraically, ideally it's best to draw a picture. If you're given all the vectors in IJK notation, you don't even have to draw a picture, to be honest with you. I still would do it because it protects you from making careless mistakes. But the main thing is you don't have to. You can just add all the I components because they all look like components, and then add all the J hat components because they all look like components, and then put your answer to the sum of the I components in front of I hat, put a plus symbol, and then put your answer after the plus symbol and in front of the J hat. So that all works. But what we're doing when we do this algebraically is we're attempting to find each of the components of the vectors according to the coordinate axis that we've chosen. So I chose X is pointing to the right and Y is pointing up. So I have to find sort of the shadow of the A vector on the X axis and the shadow of the A vector on the Y axis. That's what those components are. Does that make a little bit more sense metaphorically, maybe? And the way we do that is knowing our basics of trig. Some old horse came a hopping through our alley, or so ka toa. Either of those works. You've got to try to use the smallest angle or the angle between the vector and the closest component, or excuse me, the closest axis. You could use to the further axis and they would still be under 90 degrees. So that's fine. But definitely you don't want to get in the spot where you're using angles that are bigger than 90. You could, but you got to be careful with that kind of stuff because it's sort of unphysical. You're not looking at an actual diagram. You're not looking at an actual triangle. Let's put it that way. So that's what I did with vector A. I saw that I had a positive X component, a positive Y component. And if I just took the time to take the sine of 60 degrees, I'd know that would be AY over 20 meters per second. So if I multiplied 20 meters per second times the sine of 60, that should give me 17.32 meters per second. Similarly, if I took the cosine of 60 degrees, that should give me AX over 20 meters per second. So 20 meters per second times the cosine of 60 should give me 10.0 meters per second. Notice it's not spitting out any signs. I want to be the one to put the signs on there, and you should be too. Okay. Then for vector B, we see that's technically in the second quadrant. So if you happen to remember those rules, you could do that. But I really don't think that's a useful thing for you to take time and memorize signs for each individual quadrant. That's just goofy. We can actually just imagine walking from the tail of the vector to the head of the vector, and you'll see that you have to go up along the y-axis and left along the x-axis, so you automatically get a positive y and a negative x, and there's no memorizing of signs for any reason. In this case, the angle's 36.87 and the magnitude's 25. So you could just blindly take and say sine of 36.87 is bx over 25. So I multiply 25 times the sine of 36.87, and that should give me 15, which I have to force to be negative. Check it if you want. Similarly, I can say that the cosine of 36.87 is adjacent over hypotenuse, so that's by over 25. So if I took 25 and multiplied that by the cosine of 36.87, I should get 20. Similarly, for vector C, I saw the angle was 45. I take the sine of 45. That's got to equal CY over 14.14 meters per second. So 14.14 meters per second times the sine of 45 should give me 10. I have to force that to be negative. Similarly, cosine of 45 has to be CX over 14.14 meters per second. So 14.14 meters per second times the cosine of 45 should give me 10, which I have to force to be negative. And then finally for vector D, I'm going to take the sine of 36.87 and set that equal to dy over 25.0. So dy should be equal to 25.0 times the sine of 36.87, which hopefully you got was 15.00, and then I got to put the negative on it. If I took the cosine of 36.87, that would have to be dx over 25 meters per second. So 25 meters per second times the cosine 36.87 should give me 20, which I had to force the positive, but that's it. Now I just have to add all the x components to get the x component of the resultant, and I have to add all the y components to get the y component of the resultant. That's what I did with the two tables down there. And then I just draw them with the x component. I usually draw them tail to tail there. You could draw them head to tail. That's fine too. And then you have a right triangle that you can use to find the hypotenuse and the angle. So does that make sense to everyone?
Can you clarify that the when you're writing your signs, that it's where like you're at the head of your arrow ends up, like whatever quadrant, not like the direction it goes, but it's where the head of your arrow ends up is the
Gotcha.
sign that you get.
So yeah, let me look at some specific vectors. So what I'll do is I'll draw a coordinate or coordinate axes again. Like this. Okay, let's start off with this vector. Okay. So what I want to do is walk along parallel to what is the x-axis and parallel to what is the y-axis. And I need to go from the tail to the head. So if I choose to do that, then this guy, I have to walk this way first. And then I have to walk this way. So that forces this one to be positive because it points to the right, and that forces this one to be positive because it points up. Notice if I would have done this one first, I still would have pointed up. And then this one, I still would have pointed right. So there's really no way you can do it quote unquote wrong unless you just don't understand that you need to imagine the walk from the tail to the head. Now, if I do another vector, let's say this guy, okay, I'm going to walk from the tail to this point. That's a positive direction, but I'm going to walk now to the left, and that's a negative direction. That makes sense? If I did this one, I would see that I have to walk that, which is a negative direction. Then I have to walk this, which is also a negative direction. So you can see how you can actually build that memorization that they gave you in trig. You know, plus plus, negative plus, or plus minus, minus minus, and then plus minus, you know, that kind of thing. Let's do another one here. So in this case, I'm going to go down, which is a negative direction. But then I'm going to go to the right, which is a positive direction. So this is positive, and this is negative. Did that help you, Hannah? Okay. So yeah, that's the kind of stuff you want to do. Notice every time I'm forcing myself to use this itty bitty angle. In principle, I could use the other angle too, but if I use this angle, notice the triangle's not wrapped around it, so it looks a little confusing. But if I go back and drew the red down and then the red to the left, you'd see I get another triangle. And in fact, the sine would give me what cosine gave me before, and the cosine would give me what sine gave me before. That's what it means to be co-angles, is the trig function of the complementary angle. That's why you have a cosine with a sine, and a sine with a cosine, and a tangent with a cotangent. Any questions on that? All right. So you can also tell, if we go back and look now at that multiplication thing, when I did the vector 2a, notice the vector a, if I go from the tail to the head, I make 2 blocks to the right, and then I make 2 blocks up. So the x component of a is 2, and the y component of a is 2. Notice what happens with 2a. I have to make 4 blocks to the right and 4 blocks up. So that tells us that if I multiply a vector by a scalar, say 2, then that scalar has to be distributed to each of the components. That's where this notation right here comes in. Because if I put a 2 in front of that, it makes perfect sense that the 2 has to hit the 5, and then the 2 has to hit the 12.32. Does that make sense? All right. So we've actually finished what I wanted to get done. We've done basically everything we need as far as the vector goes. The projectile motion is a little more complicated, but I planned on go ahead and spending Wednesday on that. What this means is your first face-to-face test will just cover chapters 1 and 2. Okay. Your second face-to-face test, of course, could be anything, but you know, depends on how many chapters we've gone through. But we already had our online test that was 2 chapters. That was due last night, 11:59. Now you have a face-to-face test. For those of you who have lab, don't y'all have lab on Thursday? Okay. I just wanted to double check that. What I did was I took the exact same practice test that we had for the online test, and I changed its name. So if you now look on practice test module in Canvas, you'll see there's practice test 01, chapter 1 and 2, and that disappeared January 28th. And the reason why was because you were supposed to have your test 1 done by then. But now you have practice test F2F T01. That means face-to-face T01, but it's literally identical to the other test. But now you have that available to you till February 1 at like 7:10 p.m., which I think is what time your lab starts if you have that lab. Okay. So that's the test you want to take. And you want to take it because when I go through at the end of the semester, both of those will count as practice tests. And I'll take the highest score that you got on PT01, and I'll take the highest score that you got on PT F2F T01, and those will be added in the average. If you didn't do one of them, you're going to get a 0 for that, and that makes less extra credit points for you. So make sure you do that. Anybody have any questions on anything now? All right, well, you folks are free to go. I'm going to wait for the last person to leave in case anybody has any questions. Thanks
Yeah,
everybody for coming, and have
I
a
have
good
a
evening.
quick question.
Yes, sir. Go for it.
Thanks. Have a good night.
So, whenever I try to do the homework or
Uh-huh.
like log into the homework thing, modules, um, it's saying I have to like buy the book, and I was like, okay, I'll just do that, and then I'll try to hit like click to purchase it, and then it locks me out for 25 minutes, and I'm like, I'm not sure how to like I've gotten on Pearson where I need to buy the book, but I don't know if there's a certain book I need to buy with a class code or anything like that or something, or
Okay, are you going, well, you're actually going to the homework links within Canvas, right?
yes.
Okay. Well, you're doing all that right. What you might want to try is emptying your cache. Sometimes that can cause little problems. And then try going back and hopefully it won't lock you out. Otherwise, I just call Pearson support. And
Okay.
once you get all that straightened out, let me know and I can give you credit for any deadlines you missed for the homeworks. But the main thing is you need to be able to do homeworks for the test or you're going to be
Yeah.
shot in the foot. Were you able to do the test one online? You don't have to tell me your score because this is in front of the
Yeah.
internet and everybody.
It's like when I try to click buying it, it says using the browser back, close or refresh button will lock your Pearson account up to 25 minutes. Leave, please use the cancel registration button.
It sounds like you might have pop-up blocker on because
Hmm.
a lot of my lab and mastering pops up pop-up windows. So what
Yeah.
might be happening is that window is trying to pop up and then your browser's saying no and it's telling you, oh, well, if you're going to do that, you're going to get locked out. So you might want to allow pop-ups from the My Lab and Mastering website. But I would definitely go ahead and call them. This is probably a decent time because My Lab and Mastering is now 3-4 weeks in. So they probably don't have that terrible of a line. But yeah, I'd definitely call them and
Yeah.
find out. But first thing I'd try is check and see if you can turn up pop-up blockers off at least while you're on that site, and empty the cache. And I bet you everything will work there. And you can buy it right from that site. You don't need to go to the school or buy it. In fact, you'll get a cheaper deal if you buy it there.
Yeah. Okay. All right.
Okay.
Thank you.
No problem. And hey, we'll look at your scores if you screwed up, like if you didn't make that well of a good of a score on open online test one. I'll see if there's something I can do to make up for that for you since you had those problems. But definitely let me know a little earlier in the future, or your instructor know in the future.
Yeah, I just had this problem over the weekend
Oh,
when I was
okay.
trying to do homework. So, all right, thank you.
Good luck, Caden. Anyone else? Jonathan, Hannah?
This is more of a it just relates to me question because I'll be attending. So will my practice test for face-to-face practice test disappear Thursday before my lab?
Okay, you are in. Ah,
I'm technically in the Thursday lab section on Canvas.
okay, so you're in the NO2. Ooh, let me check real quick. I want to see something.
Okay. I mean, I have a tutoring appointment on Friday, so I was hoping to work with her on that, but I can always move it up.
Ah, okay. So I just looked. You're in my N02 PHY 241. So that actually holds for you. That
Okay.
it'll be open till Thursday. If you're wanting to attend my lab, which I think at one time you were considering, then you just need to not take that test after you've actually had it. In other words, because ours will be on Wednesday as opposed to Thursday.
I thought it was Monday because I came to your lab this morning.
Yeah. Oh, I'm sorry. I was thinking you were 242. This is 241.
Okay.
That's right. Yeah. So you, I'm sorry. I've been drinking. No, no. So yeah, our class meets on Mondays, and it won't be until Monday of next week. So what you might want to do is remind me Thursday that you can't access it anymore. If you're going to take it at Thursday at their lab, that's fine. You can go ahead and do that, and you don't have to do anything. But if you want to wait and take it Monday with my lab face to face, then you might want to remind me Thursday that hey, I can't access my test anymore, and I'll just open it up for you till Monday.
Okay. Yeah, that works. I will come to your lab Monday because my other classes start on Thursday night, so I won't be able to go to that lab
Okay.
anymore.
Gotcha.
And I think it'd be good for me to be able to work over it over the weekend too after I take it on Friday.
Yeah, I
Because you
agree.
can take it multiple. You can. It's the same thing as face to face. You can take it like multiple times till however many times you feel comfortable.
Not the face-to-face test, but the practice test you can.
The practice test. Okay.
Yeah.
'Cause
And the
is there a
online
face to face?
test, you can take it 3 times.
Is there a face to face practice test?
Yes, that's the one I just made. It'll
Okay.
say F2F in the title.
All right. So there's same as the online face to face practice and face to face test.
Exactly.
Okay. Perfect. Alrighty.
All right. See you, Anna.
Thank you. Bye.
Anyone else? Well, thank everybody for coming. I believe the name is Hind or Hind. Anybody have any questions? Yes. You want to type it? You might not have a speaker, so I see you're chatting. Gotcha. Is it Hind or Hind? Or am I way out in left field? Sure. I. Gotcha. Did you have a question? Something I can help you with? Yes. Yes, the online test. And I had made some announcements to class and all that kind of stuff. Are you the person that sent me a text message about it last night? Okay. I got a text message last night, but I went to bed so early I didn't see it till like 5 o'clock this morning. Uh, I'm assuming that means you might have missed the first online test. Okay, I can open that back up and give you I will open up the practice test and the online test and give you until Wednesday to get that done. That work? I'm gonna do that for anybody else that missed it too, just to be fair, but I will do that. All right. Well, have a good one, sir, or or ma'am or whatever. I don't know. Sorry, ma'am. Thank you. I feel so inclined to, say that to people, but I don't know anything. Thank you. You have a good one. Bye, everyone. Bye bye. That's my bad shoulder. Can't lift it up.